Welcome to day 4 Piecewise functions. Today we're going to graph and write equations for piecewise, and we're going to determine limits from those piecewise functions. So I think you've done a piecewise function before in Algebra 2. A piecewise function is a function that uses different formulas on different parts of its domain. So basically a piecewise formula looks like this: f of x equals, and usually you start with a squiggly bracket, and we have formula number 1 for domain number 1. And then we have formula number 2 for domain number 2. And we could go on and on and on. We could have more formulas. The domain is for what x values that we're going to do the graph for, and the formula gives us the y values for those given x values. We've actually seen a piecewise function before. A good example of one is the absolute value of x, this v-looking graph. Even though it's just one graph, we could make it into a piecewise formula, because right down here, right down the middle, at x equals 0, which I call a boundary, you can see there's a left piece and there's a right piece. Okay, the left piece, I'm going to bring a different color. The left piece is y equals negative x, negative slope going downhill through the origin, and the right piece looks like y equals x, starting at 0 and going out to infinity. So another way to write the absolute value of x would be write it as a piecewise function in two different pieces, where right here I'm going to split it in half. This is my left piece to the left of x equals 0, and this is my right piece to the right side of x equals 0, including 0. I could have switched it. I could have put including 0 on the left piece and not including 0 on the right piece. You know, it doesn't really matter. So let's look at an example of drawing a graph of a piecewise function. So you can see that this piecewise function g is split into two pieces, a left piece and a right piece, and x equals 1. As you can see, this says to the left of 1 and this says to the right of 1. So x equals 1, I'm going to draw it as a dashed line. This is not an axis of symmetry where we could do quadratics. I'm using x equals 1 as my boundary. So here's my left piece I'm going to do, and here's my right piece that I'm going to do. Well, what I made it nice was that both pieces are just lines. So what I should do is probably use, first I should use x equals 1 into the left piece. I plug 1 in here, I get 3 times 1 minus 5, I get negative 2. And I'm going to have to use any number to the left of 1. Any number you want. You could use 0. Plug 0 here, we get negative 5. So it gives me the point 1, negative 2, and 0, negative 5. But because this point is on the boundary, a point on the boundary could be an open or closed dot depending what's given to us. So if we look carefully, this says x is less than 1, so I never really use 1. I get really close to 1. So the point 1, negative 2 should not be a closed dot. It should be an open dot. So I'm going to make an open dot here. And then what I can do, once I have 2 points, I'm going to draw only on the left side of the boundary. I could go down 3. And here is my left piece in black. Now my right piece I'm going to do in blue. It says x is greater than or equal to 1. So again, I'm going to plug in 1. I plug in 1. I get 2 as a result. I can plug in any number bigger than 1. So I may as well just plug in 2. I get 0 as a result. So I'm going to plot the point 1, 2 and 2, 0. And I should pay attention. The point on the boundary could have been open depending what the stipulation was. And it says x is greater than or equal to 1, so I'm including 1. So there's a solid dot here at x equals 1. I have 2 points. I could go more, slope of -2, just to give me some more thought. And I'm only going to draw the blue graph on the right side of the boundary. So this was my right piece in blue, my black piece in left. So this was a closed dot, and 1, 2 was an open dot because it was not included. And now I could determine all these values. So when I do g of -5 is less than 1, so I'm going to use the left piece. So I do 3 times -5 minus 5 is equal to -20. So this is -20. Now when I use 1 is right on the boundary, but which piece uses the x equals 1, the left piece or the right piece? Well, this has to be the right piece. So I have to do 4 minus 2 times 1, and I get 2 as a result. Okay, 10. Again, 10 is bigger than 1, so I have to use the right piece. So that equals 4 minus 2 times 10, which is -16. And then I say equals 0. So g equals 0, this is a y value equals 0. One way I could look at the graph. I could draw the horizontal line, y equals 0, and I can notice that when I do the horizontal line, y equals 0, it only hits the right side. I could go ahead and solve for that. 4 minus 2x is equal to 0, -2x equals -4. I get x equals 2. And then I have the same thing here I draw it light blue. This is a y value of -8, and right here is -8. Y equals -8, and I could see that it hits the x here and hits the x here. I could just look at the graph if I had to, but if not, I could just solve them. So I could do the left side, I could do the right side, and on the left side, it's 3 minus 3x minus 5 is equal to -8. Add 5, 3x is equal to -3, x equals -1, and it does hit right here at x equals -1. And on the right side, I could do 4 minus 2x is equal to -8. -2x is equal to -12. Divided by -2, x equals 6. I do see it does hit at x equals 6. Now let's look at domain and range. My domain for this graph is all the x values left to right, and it goes from -infinity all the way up to 1 very close, but this is a solid dot at 1. So it does include all real numbers. And then the range is the y values, and it starts here at -infinity. Goes all the way up to -2 here is an open dot, but the blue one covers that. So the range would be -infinity to all the way up to the solid dot here, including that solid dot. So let's do this next graph. This h function has 3 pieces. So I'm going to split it into 3 pieces. And the boundary for the first piece is x equals -1. So I'm going to draw a nice little boundary at x equals -1. And the other boundary is x equals 6. So I draw another boundary at x equals 6. And I have a left piece, a center piece, and a right piece. So for my 3 formulas, I have a left, a center, and a right. I broke up my graph into left, center, and right. So this first piece here, this first formula here, next to the blue L, that's a parabola. I only could draw that on to the left of -1. Well, to me, when I look at this in vertex form, I see my vertex is equal to -3, 5. So at -3, 5, I have my vertex. And then, oh, I have an a value equal to -2. It's going to be a concave down parabola. So I could just count my squares. I could go over 1 square. And 1 squared is 1. Times a is -2. So my next data is right here. Here's my buddy point on the other side, because there is a little mini axis of symmetry down the middle here. So they gave me the points -2, 3. And then the next point I'm going to do, I'm going to go back to the vertex. I'm going to go over 2 squares. 1, 2. 2 squared is 4. Times the a value -2 is -8. 1, 2, 3, 4, 5, 6, 7, 8. But it's on the boundary. So I have to ask myself, open or closed? And I see it's less than -1, not including -1. So for me, I have the point -1, -3 as an open dot, and then its buddy point over here would be -5, -3, but only a boundary point could be open. Any other dot on the graph is going to be closed dot, and I have my parabola that looks like that. That is the left piece of the graph. The center piece, it just says 4. That's just a horizontal line of y equals 4. And right here, if you notice, at -1, so -1, 4 is going to be a closed dot. And then here at 6, 4, that's going to be an open dot. So -1, 4 is going to be a closed dot. 6, 4 is going to be an open dot. I'm going to draw a nice horizontal line between them. And that is a center piece. That's pretty easy. And then this last piece, the right piece, again, is a line. Now, normally when you graph this line, you would start at y-intercept of 1 and go up a half or 1 over 2. But I can't do that because this right piece starts at x equals 6. So I'm going to plug 6 in here. 6 times a half is 3 plus 1 is 4. But it's not including 6, so 6, 4 has to be an open dot. I already have an open dot here at 6, 4. And then I could pick up any value bigger than 6, or I could just do a slope equal to a half. So I could go up 1 over 2 and put some solid dots, or I could pick a number like 8, plug that in here and get 5. And I get all that. And now I have my right piece. So the left piece is a concave down parabola. The center piece is a horizontal line. And the right piece is a upward diagonal line. Now I could do my limits looking at this graph. So right here, -1, on the left side of -1, that's the blue graph, is the left side of -1. The left side stops here at -3. The right side of -1 is this green graph, and it stops here at y equals 4. Well, since these two do not equal each other, when I do -1 from both sides, that's D and E. And this is a value question. It's looking for a solid dot, and the solid dot at x equals -1 is positive 4. Now at x equals 6 from the left. 6 from the left is the green graph, and the green graph stops at y equals 4. as x approaches 6 from the right, that's the red graph, and you follow the red graph back to x equals 6, you get y equals 4. Since these two equal each other, when I do both sides, the left and right side, the green and the red are meeting together at y equals 4. And then x equals 6 is looking for a solid dot. Well, there is no solid dot, so this is undefined. Now I have to do my domain. My domain looks like it should be all real numbers, so it looks like this graph goes completely left to right. But there's an open dot here, but there's a solid dot here at x equals 1, so that's covered. But over here at x equals 6, there's just an open dot. So my domain is negative infinity to 6, union 6 to infinity. And my range, which looks like this graph goes down forever, and it goes up forever, and it covers everything in between, is negative infinity to infinity. Now it looks like we're going to write the equations of the piecewise function. So when I look at this graph, right down the middle here, at x equals 0, I have a left piece and I have a right piece. So when I do this, I'm going to have a left piece, I'm going to have a right piece, and the left piece is going to be for x less than 0, and the right piece is going to be for x greater than 0. And we'll decide later which one's going to have the equal sign, because for this one I don't think it really matters. Now the left piece, this left piece is a parabola. And to me, I could do it either way. Well, I think I can only really use vertex form, and my vertex is negative 1, 4. So my parabola is going to use y equals a x plus 1 squared plus 4 when I use vertex form. But I see there's another dot on this graph right here, 0, 2. So I'm going to plug a 0, 2 into this. I get 2 is equal to a 1 squared plus 4, which is equal to a plus 4, because 1 squared is 1, or you could call it 1a plus 4. I can subtract the 2. I get a equals negative 2. A better be negative 2 because this is a concave parabola. So I'm going to take this formula and rewrite it in the piecewise negative 2 x plus 1 squared plus 4. So I'm doing this left piece. I'm going to erase this. For x is less than 0. Now the right piece is just a linear function. And I see I have a point here and a point here. So for the right piece, it's a line. And I think when I look at this, I see a y-intercept of 0, 2. If I count my slope, I see it's up 1 over 3. So slope of a third. And it goes through the point 0, 2, which is a y-intercept, so I could just use y equals mx plus b, or 1/3 x plus 2. So this is 1/3 x plus 2 is my equation. And I'm going to do that for x is greater than 0. And since there's a solid dot here at 0, 2, and both graphs have 0, 2 on them, it doesn't matter which one I pick, where I put the equal sign for the 0. I could do it with the red or the blue, because I'm just going to choose for the blue now. It doesn't really matter. And finally, for this second piecewise function, it looks like we have two pieces, a left and a right. It looks like for the left piece, it's for x is less than, the boundary is right here at 3, and there's an open dot on the left piece, so there's going to be less than 3. And for the right piece, it is not going on forever, so it's going to be from 3 is less than or equal to solid dot x less than or equal to, and it stops here at x equals 10. So those are my two pieces, the left piece and the right piece. Well, this left piece is a parabola, and I don't think I have a good clean vertex, but I do have nice clean x-intercepts. So my x-intercepts are 2 and negative 5. So I could do y equals a x plus 5 x minus 2 by using my factored x-intercept form. And then I see there's another point on this graph right here, and that point is at 0, 5. So now I could write 5 equals a, plug in 0, 5 times negative 2, 5 equals a times negative 10, divide by negative 10. I get a equals negative 1/2, and I better get a negative. This is a concave down parabola. I could do that over here for the left piece. Negative 1/2 x plus 5 x minus 2, and it is for x is just less than 3, not including 3 because there's an open dot there on the boundary of x equals 3. Now this right piece is also a parabola. And again, I don't think I really have nice vertex right here, but I do have nice x-intercepts of 3 and 6. So I could do y equals a times x minus 3, x minus 6. That means I have to find one other dot on this graph, and I think there's another clean dot right here at 8, 2. So I plug in 8, 2 in for the x and y. I get 2 is equal to a, 8 minus 3 is 5, 8 minus 6 is 2, and I get 2 is equal to a times 10 divided by 10. I get a is equal to 1/5, and it better be a positive value. This is a concave up parabola, so it's going to be 1/5 x minus 3 x minus 6. That is the equation of that right side of the right parabola, and it's going to be for 3 less than or equal to x less than or equal to 10, because I have two solid dots, one at x equals 3 and one at x equals 10. So we've gone through graphing piecewise and writing formulas for piecewise.